Alright, so it's time for our last video in this flipped classroom unit on light and optics. And this last video will be about light and how it's part of a bigger thing called the electromagnetic spectrum. So let's get stuck in. So if you cast your mind back to our video on polarization, you might remember that light is an electromagnetic wave, or EM wave for short, and that it's made out of two things: an oscillating electric field and an oscillating magnetic field. And that those electric and magnetic fields are at right angles to each other, as shown in this diagram here. And they're also at right angles to what we call the direction of propagation, which is the direction that the wave is moving in. So you can see here, electric field that way, magnetic field that way, wave moving that way. So it's this fact that light's made out of electric and magnetic fields that allows it to travel in a vacuum, whereas other kinds of waves like sound waves cannot. If you do physics next year, we learn more about that in stage 2 physics. So here's just a quick little animation that I got off YouTube showing what I'm talking about. So here's your light wave made out of oscillating electric and magnetic fields. And you can see that they're oscillating in a direction that's perpendicular to the actual way that the wave is moving. Okay. So all of the different kinds of electromagnetic radiation, which includes light, put together forms what's called the electromagnetic spectrum, or EM spectrum for short. Now, visible light only makes up a very small portion of that, from 400 nanometers, which is violet, up to 700 nanometers for red light. And you can see in this diagram here that as you increase, as you increase the frequency, the wavelength obviously decreases, but you also increase the energy as well. So things like gamma rays and X-rays will have a much higher energy than things like radio waves over here. So we're going to have a quick look through the different parts of the electromagnetic spectrum and a few interesting facts about each part. Except for visible light, which we've covered in so much detail, we're just going to leave that out. We'll look at the rest of the electromagnetic spectrum. So going from the smallest frequency and least energy, we start with radio waves. Now, obviously, radio waves are used for transmitting radio, but they're also used for carrying TV signals as well. And the reason we use radio waves for that is they have a long wavelength, which means they can travel longer distances before they sort of fade away than other sorts of electromagnetic radiation. And they're also really good at bending around obstacles. So TV transmitter can be on one side of a mountain, person with a TV set can be on the other, and most of the time you can receive some sort of a signal, so the radio wave will bend over the top of the mountain and down the other side. Other sorts of electromagnetic radiation like light won't do that, so it has to do with that long wavelength. And as well as that, we also use radio waves in two sort of things that you may have seen in day-to-day life. What's called a radio frequency ID tag, or RFID tag. Now that's shown up here, here and here. So this first one here, you may have seen that in some things like books. Inside the books at bookstores, you'll often see a sticker like this, and that's basically designed so that when you take it, if you try and steal the book and you carry it out through the door, this little radio aerial here basically will set off a signal, and that'll set off the theft alarm. So that uses RFID. That little chip in there is basically the RFID chip. This thing over here is called a Mikey card. That's what they use in Melbourne to pay for public transport. Inside that is another little RFID chip that uses radio waves to talk from the card to the scanning device on the bus or the tram. Then you also have these little key fobs down here as well, which again contain the RFID chip, and you can use them to unlock doors. In fact, many of the doors at Marrickville High School, you have to open them using one of these little RFID fobs here, and I have one of those to get into the main sort of office block of the school. And then a newer sort of thing that also uses radio waves is what's called near field communication, or NFC tags. Now, one of the main applications for that at the moment is inside mobile phones. So if you've ever used like a tap to pay thing, like what we've got here, or you've done the thing where you take two phones and you sort of hold them together like that to transfer files between each phone, then you've used this NFC thing. It's a kind of radio, but it only works over a very, very, very short distance. So for example, here this person is using tap to pay, but they have to hold their phone right up against the ATM thing there, otherwise it won't work. So both RFID and NFC use forms of radio waves as well. Okay, from there we go up to microwaves. Now microwaves are used for many things. Probably the main thing we use them for these days is for mobile phones. And we use microwaves for two reasons. Firstly, that when you compare them to radio, they have a shorter wavelength, which means that the antennas used to pick them up will be shorter as well. So something like an iPhone can fit its antenna inside the case, whereas if you had to use radio, you'd have to have like a big, long, extendable antenna, a bit like what you have on a car. And then the second reason we use microwaves for mobile phones is they have a higher bandwidth, which basically means you can put more information into a microwave signal than you can into a radio signal. Radio signals can't carry as much information, so if you want to do something like download a file over the internet using your mobile phone, it's going to take a lot longer if you use radio waves because the data just doesn't transmit as fast. And other applications as well, the Bluetooth in your phone uses a kind of microwaves, and your home Wi-Fi uses microwaves as well. And obviously, one application of microwaves is in microwave ovens. Now, microwave ovens basically use the same kinds of microwave energy that you use in mobile phones, but to actually make it sort of heat things, you have to trap it inside what we call the cavity of the oven, and you create standing waves. Oops, go back a bit here. I think I've missed the page I was after. No, it's gone. Okay, so you get standing waves inside the cavity of the microwave. And one of the other reasons we use microwaves is because the frequency of microwave energy, which is about 2.45 gigahertz or 2.45 billion hertz, is equal to what's called the resonant frequency of water molecules. That's the frequency that water molecules like to vibrate at. So if you put something that has water in it inside a microwave, you're going to make that water molecule vibrate because the frequency of the microwave energy used is the same as its resonant frequency. And as it vibrates, like so, backwards and forwards really rapidly, that's going to heat up the molecules and therefore heat up the food and cook it. So a quick little video here to basically demonstrate how these standing waves form inside a microwave. You can't see them, but if you put something that can use the microwave energy to produce light, like this little row of LEDs here that the person's made, the LEDs will light up at the points in the microwave oven where you have the antinodes of the standing waves, where you have the most energy. So this person's made a little grid basically of LEDs. They've chucked it on the turntable in their microwave. And then we'll see that as the microwave is running and the turntable rotates those LEDs through the different parts of it, when the LEDs get to a point where there's an antinode, they receive enough energy to light it up. So that's basically a nice little demonstration of the fact that there are standing waves within a microwave oven cavity, and that those standing waves are standing waves of microwave energy with a frequency of 2.4 gigahertz. Alright, so from there we go up, and then the next one is what we call infrared. Now infrared is just below what a human being can see. It's just below red. Lower frequency than red and a slightly longer wavelength. Now infrared, it turns out, is produced by hot objects. So it's used for what we call thermal imaging. So this little video here shows what you'd see through a thermal imaging camera. Now what the white parts in here are the hotter parts and the darker parts are the cool parts. So this guy here, don't know what the hell he's doing, but this guy here obviously is warmer than his surroundings, so he appears as a white object on that video. Now there are some animals that use infrared as well. Snakes, for example, can see a little bit of infrared, so they can use that basically to, a bit like thermal imaging, to detect an animal that's releasing heat and hunt it down. So that's kind of how they hunt mice at night. Another application for infrared is in remote controls for TVs. Basically, a TV works with a little remote infrared LED in the front of it, and that infrared LED flashes on and off really, really quickly to produce pulses of light that are detected by the TV using a thing called a photodiode, which is basically an infrared detector. But I'll get this guy to display. So here I have the remote control for my TV, and if you look at the end of it, you'll see that there's a little LED mounted in there. Now that's the LED that produces the infrared light that's used to control the TV. Now, obviously I can't see that with my own eyes because my eyes aren't sensitive to infrared light, but any sort of device that has a little miniature built-in digital camera, like a smartphone or a webcam like on this laptop, uses a little thing called a CCCD sensor to pick up light and to turn that into an image. Now, it turns out that those things are really sensitive to infrared light as well as visible light. And in fact, you have to put filters over the top of them to try and block out infrared light. Otherwise, you'd definitely be able to see a clear image when you try to take a film or a picture with that CCCD sensor. So if you look really carefully at the sort of little tiny buttonholes for those cameras, you can normally see sort of like a purpley sort of sheen over the top of it. That's the filter that's designed to block infrared light, and it does a pretty good job. But even still, most of the infrared light will, some of the infrared light will get through. So basically, if I point this at the webcam, and I press that, I can see the infrared light being produced by the LED. Not much of it, because most of it's blocked by the filter, but I can still see it. And you can see that when I'm pressing that, I'm not pressing the button again and again and again, I'm just holding the button down. And that flickering is a pulse of infrared light sort of switching on and off rapidly, and that's how the signal is encoded. Each button sends out a different string of on-off pulses of infrared light. So this works just as well with your smartphone as well, so if you want to try this at home, grab yourself something like a remote control, like that, point it towards your smartphone and press it, and you should see sort of, this one looked like it was blue light. My phone tends to see purple light. You should see some sort of flashing going on there. And that's the infrared light getting through that filter and being detected by the sensor in your smartphone's digital camera. Okay, wise words from that guy. We also use infrared LEDs for security cameras as well. So the idea is if you're trying to see something in the dark, you can use infrared LEDs to illuminate that area with infrared light that can't be seen by a human being but can be picked up by a specially designed camera. So it allows you to basically shine light on that area without potential burglars realizing that there's cameras there because they can't see the infrared light. So you can see this camera here has a whole bunch of LEDs surrounding it. Those LEDs release infrared light, which then illuminates the area a bit like this picture here, and then that infrared light is picked up by the camera in the middle. So I got interested in that, and I went and built a little kit like this, which is basically a whole bunch of infrared LEDs on a board, which is then connected up to a power supply. And I shot this little infrared selfie, basically. So this is my bathroom at home. There's my infrared sort of lamp thing. Now again, you can't see that purple color with your own eyes. It's only visible through the camera. And now if I turn off the lights, pitch blackness, the camera's still running. And then if I grab the board, you can see that I can illuminate my face with that. And the camera picks up the infrared light that's being shone on it. Not very well. If I had a proper infrared camera, it would be much, much brighter than that. But I can see bits of it. Now I should probably say that I could not see anything. That was pitch blackness. I could not see anything myself with my own eyes. The infrared light is only visible because we have a smartphone that's sensitive a little bit to infrared light. Okay, so after infrared light, you got your visible light, but we're not going to talk about that. And then after the visible light, the next thing up is what we call ultraviolet or UV light. Now UV light is higher in frequency than violet, so it's just above the range of human eyesight. But there are other animals, such as insects, that can see UV, and many flowers have markings on them that are only visible under UV light, and that they're there to attract insects, to make them stand out and make the insects more likely to land on them and to collect pollen. So you can see some of these flowers over here. That's how it appears under visible light. That's under UV. You can see it has extra markings. Visible light, UV, again, extra markings. Now, UV is the first kind of electromagnetic radiation we've encountered in this presentation. That's what's called ionizing radiation, which means it can ionize human tissue. It can knock electrons off the molecules that make up human tissue and turn them into ions. And as you should know from chemistry, when you have ions, then you have chemical reactions. So ionizing radiation can damage the human body by ionizing molecules and causing them to react chemically in ways they're not supposed to. And that's basically how sunburn works, because sunlight contains a fair amount of UV light. That UV light, particularly in summer, is quite dangerous, and if it hits your cells, it'll cause ionizing radiation damage which kills the cells. So moving on from UV up to higher energies, we now get into what we call X-rays. So I'm sure you're familiar with X-rays. X-rays carry enough energy they can penetrate through the human body, pretty much go straight through it. They're only really absorbed by denser materials like bones, teeth, or metals. So we've got like an X-ray image here, which illustrates my point perfectly. So this poor little dog here has managed to swallow his owner's keys somehow. So you can see that the keys there stand out dramatically because they're made of metal, and that metal has absorbed the X-rays that have tried to pass through it. You can see that the bones stand out and the teeth stand out. The actual flesh itself is not particularly visible, and that's because the bones, the teeth, and the metal here absorbed a great deal of X-rays, but the X-rays that hit the actual fleshy part of the dog more or less just pass straight through and leave very little trace, only a faint outline. And that's all because X-rays have such high energy. Basically, as you go up in energy, the light penetrates further. So UV was the first kind of ionizing radiation that carried enough energy that it could penetrate a few millimeters into human skin and cause sunburns. But once you start getting up to X-rays, then the X-rays can basically pass most of the way through the human body without being blocked, unless there's things like bone or teeth there. And then from X-rays, we finally get to the highest energy form of electromagnetic radiation, which is what we call gamma rays. The gamma rays pretty much pass straight through anything like a hot knife through butter. If you want to absorb gamma rays, you really need either several inches of thick lead or several meters of concrete. That's about the only thing that will block gamma rays. Other than that, they'll just go straight through. So where do gamma rays get produced? Well, they're produced in nuclear reactions. Nuclear decay produces gamma rays sometimes, and also nuclear fission, like you have in a nuclear reactor, also produces large quantities of gamma rays. And that's the reason why nuclear reactors have to be encased within basically like a little bunker made of really, really, really thick concrete, like meters thick concrete. And the reason for that is the gamma rays that are produced are lethal in high quantities, and you have to have that nuclear reactor inside a concrete bunker to sort of prevent the radiation from leaking out. So here we got a picture of a typical sort of nuclear reactor core here. Now the blue glow, people think that that's caused by sort of like the gamma rays. That's not the case. It's caused by another thing called Cherenkov radiation. Quite complicated, we won't go into it here, but basically that's what's causing the blue glow there. The actual gamma rays themselves, their frequency is way beyond what the human eye can see, so we can't actually observe the gamma rays being produced. And then the other thing that produces gamma rays is black holes. So when a black hole is sort of sucking in material, like what we have down here, we've got a black hole that's near another star, and it's sort of dragging gas off that star and sucking it inwards like a spiral, a bit like water going down a drain. As the material gets sucked inwards, it sort of produces these jets of high energy particles and radiation that fly out either end of the black hole. So they're not escaping the black hole, it's more like these jets of matter and radiation are produced by the material just before it goes into the black hole, and they shoot out either side. And that whole thing put together, the black hole plus the accretion disk, this basically disk of matter that's being sucked in, and these plumes of high energy radiation produce what's called a quasar, which is short for quasi-stellar object. And the ends of these quasars that fire off are very, very, very high in gamma rays. And sometimes, if one of these is pointing towards the Earth, we can pick it up using like some sort of gamma ray telescope. So luckily, we're very far away from the nearest sort of black hole. If we were near a black hole that was behaving like a quasar, and one of these jets was to actually point towards the Earth, the radiation released by that jet would be enough to destroy the Earth in a second. It's pretty insane. And that is it for this flipped classroom unit on light and optics. That was our last topic. So I'm going to sign off, say goodbye, and just a little bit of a physics joke here for you, if you can work it out. See if you can work it out. All right, I am done.